Hi, I'm Yonghwan from South Korea. My team and I are master students in Seoul National University Virtual Machine and Optimization Laboratory. This slide contains a brief bio of each team member and their role in the project. Now let's get started with the main agenda. Micromobility, or personalized mobility, is often thought of as the future of urban transportation. Thanks to their portability, these vehicles can better connect people to public transits and fill those first and last miles in our daily transports. This new mobility trend is coming to us in many forms, including the electric scooters, which started the scooter sharing hype in many countries, including America and South Korea. In 2019, more than 20 startups dove into the e scooter war in South Korea alone. Yet in the beginning of 2020, the number one market leader, Lime, reported that it laid off 14% of the workers and exited 12 markets, including Atlanta, Phoenix, and San Diego, because the cost of maintaining these e scooters was just not worth it. We found a similar problem with public bicycles, another form of micromobility that are usually run by city governments. Then why is it so expensive for startups and governments to maintain these micro vehicles? Let's look at the example of Seoul City public bicycles. Since many of the users usually try to park the bikes around the same area, it is inevitable that at certain times during the day, some docks will have more bikes than they can hold, while others' docks are empty. As this greatly reduces the availability of these bikes, the city officials manually collect and disperse these vehicles so that they are evenly distributed across all docks. This requires a lot of manpower and manual labor. The problem becomes worse for e-scooters, which mostly don't have designated return spots and thus require more energy for finding the vehicles in the first place. Not only that, e-scooter maintainers need to make sure their vehicles are fully charged and ready for service all the time. As a result, e-scooters need to be recollected and redistributed more frequently than regular bicycles. On top of that, some local city regulations make it more challenging to maintain these vehicles. For example, the Phoenix government policies require that e-scooters can only be picked up between midnight and 5 a.m. This is why we present Tava, a blockchain-based solution for micromobility redistribution. Tava incentivizes micromobility users to redistribute the vehicles themselves, which leads to automatic maintenance of these service vehicles. Our main strategy is to provide rewards for mobility users that help solve the vehicle overflow problem. Following is an overview of the automatic redistribution process. Whenever a user connects with an available vehicle, we run a query to our server which keeps track of the optimal vehicle count at each dock based on previous usage history. In response to the query, our server selects several destination spots that minimize unfair concentration of these vehicles. We then suggest these alternative spots along with the expected rewards of riding to those spots. This reward system can attract people who want to save their pockets to participate in the redistribution process. Moreover, as the vehicles become available at lower prices, the reward system can increase the number of new users into the mobility platform. In this sense, Tava suggests a solution for not only the mobility operators, but also for mobility users. Let me walk you through the whole idea from a user's perspective with this brief demo. After authenticating herself via Google OAuth, the client connects to one of the mobility vendors that she wants to use and inputs the address of departure and arrival. This information is passed on to the Tava backend server, which outputs the incentive that the client will receive for dropping off the vehicle at the destination. At this point, we calculate and provide incentive information of several other spots close by to the destination so that she has options for using the vehicle at lower rates. The client then makes the choice on her final destination and uses the vehicle. Later, when she proceeds with payment for vehicle usage, she proves that she arrived at the expected destination spot and receives her reward. Afterwards, she can check her transaction history in the side menu. Source code for this demo app is currently available on GitHub at the URL below. As you can guess from the demo, our service is backed primarily by two systems. First is a machine learning-based server that predicts future vehicle availability at each dock throughout the next hour. The role of this server is to compute the incentive of each vehicle ride based on that prediction, in such a way that the global vehicle availability is maximized. For instance, assume there are two vehicle docks A and B. A is predicted as a popular rental spot throughout the next hour, while B is a rarely visited area in this time period. Our server should then set higher rewards for arrivals at dock A rather than those at dock B. This diagram explains our machine learning-based vehicle availability prediction model, which takes the time and station ID information as input and outputs the number of available vehicles at that dock during the next 1 hour. As a proof of concept, we built a neural network and trained it with Citi Bike 2019 data. Our model predicts the number of available bikes with mean absolute error less than 2. The source code is provided in the link below. The second infrastructure is the Tava blockchain. Our application server interacts with Tava for the payment of a vehicle ride and also for receiving the reward for that ride. Thanks to the high performance of Tava and its Avalanche protocol, Tava is highly suitable for processing micropayment transactions initiated by hundreds of thousands of mobility users quickly and efficiently. As such, we use the smart assets of Tava blockchains for implementing bike rentals as transactions. In practice, since we compute the rewards of a vehicle ride in a machine learning server outside the blockchain, we implement an interface named PySlopes that integrates these two backends. PySlopes is a Python library for interfacing with the Tava platform. It is inspired by the actively maintained JavaScript library Slopes that allows a client to issue commands to the Tava node APIs. Since PySlopes is written in Python, it simplifies the communication between our Python-based machine learning server and an Tava blockchain node. We open-sourced PySlopes on GitHub so that anyone can use it freely. Based on these core components, our platform integrates the off-chain computation and on-chain transactions of the rewards seamlessly. In this slide, we show a sketch of our platform's micropayment transaction with the Tava blockchain. When a user connects to the Tava front-end web app, she delegates the rights on her Tava account to our app server so that the Tava server interacts with the Tava blockchain on her behalf. When the user makes a bike rental request on the front-end web app, the server makes transactions with an Tava node for micropayment and receiving rewards for the vehicle ride. Our prototype is implemented for a Gecko node, the official Golang implementation of an Tava node. We have also made some feature upgrades for the Gecko node during our implementation, which is currently being reviewed by the Gecko community. As a final step, we model the whole Tava platform as a system with a set of parameter configurations. In this way, we take into account various scenarios in which a number of users are mapped to randomly filled Tava accounts and a number of vehicle stocks that are filled with a random number of bikes. This model also takes an incentive policy as input, which decides how much a vehicle ride should be rewarded given a prediction result. Using the simulation script, one can simulate the operation of the Tava platform and observe several target metrics, such as the sum of all balances in every user's account, or the flow of Tava assets and the resulting transaction fees with respect to time. By repeating several iterations, our simulator aims to find the best hyperparameter configurations for a given scenario. Based on this simulator, we can choose appropriate incentive policies for a new mobility operator that wants to join the Tava platform. Therefore, Tava is capable of serving multiple mobility operators as client companies. To summarize, we propose Tava, an automatic vehicle redistribution platform for personalized micromobility. We built our service on top of Tava blockchain for its high throughput capabilities, as well as a prototype machine learning-based system for computing future predictions for vehicle availability. Our design aims to increase maintainability of the vehicles for mobility operators by incentivizing mobility users to actively participate in the redistribution process. We proposed an MVP implementation of the platform and opened it publicly, also making contributions to the Tava community in the process, such as PySlopes and Gecko. Ultimately, we expect that our platform will help make our future transports more available and sustainable. This is the end of our presentation, and thank you all for listening.